Calculus, this is lesson 1.4, the last part. It's the intermediate value theorem. In calculus, we always abbreviate that with the IVT, and AP knows that abbreviation. We start off with the fact that the IVT is called an existence theorem. You're going to prove that a value exists, but not necessarily how to find the value. What I have highlighted here in yellow, it has to be memorized. You have to basically regurgitate this information anytime you do one of these problems, and I'll model that on the next slide. Okay, to get you started, let me erase here. The IVT says the following. If I have a continuous curve on a closed interval, and if you watched the video from a few days ago, we showed how to show, in that video I showed how to show continuity on a closed interval. You have to basically find the limit value here from the right side of A. You also have to show that that limit from the right side of A equals the function value at A. And then we had to come in on the left side of B and show that that function value matched the limit from the left side of B. And then we had continuity between A and B. So that part's already been covered. So what we're saying here in this lesson with this theorem is that between A and B, there's some value K. So there's some Y value between A and B, f of A and f of B, such that if I extend that and make it a horizontal line, I'm going to basically intersect my curve at a point, and that point on my x-axis is called C. So basically you're finding a value on your x-axis that matches up with a y value of K. Now, if I just draw something like this, and you know that you have something like that, maybe this is A, and let's say this is B, and let's say up here, this would be f of A then, up here would be f of B. I think you can see that there's some line coming through here maybe that intersects my curve, and that line is going to be at K. The place where it intersects my curve is going to be this C value. All right. Another application of this would be looking at something like this. Let me do that differently. Hang on. Okay. Here we go. Let's go from here to here. If this is A and this is B, this is f of A here. This right here would be f of B. And you can see then that if f of A has a positive sign and f of B has a negative sign, that my curve crossed the x-axis. So you can use the intermediate value theorem to guarantee that you have an x-intercept or a zero for a function on a closed interval. So there's another side of the intermediate value theorem. All right, and that's what we're talking about here. If f of A and f of B have opposite signs, then the IVT guarantees a zero in A to B. All right, so what we did with this first problem, we said, okay, here's our function x squared plus 2x, and here's our closed interval 1 to 4. Our K is 8. So basically, before we got started, we kind of talked about it a little bit. From 1 to 4, let's see, f of 1 is 3, f of 4 is 24, so maybe it's something like this. Now, of course, you don't have to draw a graph for these. I'm just kind of illustrating what we're given. So our A and B are actually the numbers 1 and 4. And so they gave you that k is 8. So let's say that that sits right here. This is 8. So if I come across and I come down, I'm going to find this place right here. We call that C. In order to do that, you have to actually state the pieces of the theorem. You have to state that it's continuous on 1 to 4. We know f of x is continuous for a couple of reasons, but the primary one is that f of x is a polynomial, and all polynomials are continuous everywhere. And we had that show up yesterday, right? Let me keep going here. Right there. So that should have been in Part B's notes. Polynomials are continuous everywhere. So, coming back, here we are. It's continuous then on just a piece. You find f of 1 and f of 3, and then you're going to show that f of c is in between there. And I think, yeah, this 8 would represent our f of c. So you put these in numerical order. So f of 1 is smaller, so it's on the left side. F of 4 is bigger, so it's on the right side. If it were the other way around, of course, I would put the smaller one on the left. So I have to state that as well. That's this piece right here, corresponds to this right here. And then I have to find C. So to find C, I'm going to just set my equation. Oh, I missed it. Set my equation, hang on just a second. Okay, right here, equal to C. Solve it. So that work comes up here. And then I get two values that could be C, but -4 is not in my interval, so I tossed it out. So my C is 2. On this next one, I'm going to do the same thing. So I say it's continuous from 0 to 6. Now we talked about on this one that this function is discontinuous at x equals -1. That is a vertical asymptote, and that is non-removable discontinuity. However, -1 is outside of that interval from 0 to 6. So my function is still continuous from 0 to 6. It's discontinuous at x equals -1. Then I find f of 0 and f of 6, and then I state my inequality, and then I find my C value. On number 3, you have to be careful and not fall into the trap. This one is discontinuous at x equals 3. It's non-removable. It's a vertical asymptote, and 3 is actually not in, or is actually in that interval. So because you don't have continuity, you can't apply the IVT. This last one, you're just verifying that you have a 0, and that goes back to the fact that to have a 0, your function has to pass through the x-axis, which means either one of these, f of a or f of b, is positive and the other one's negative. So if my curve went up instead of down, and if this was a and this was b, f of a is here. Oops, let me do that in the right spot. F of a sits down here. F of b sits up here. We can see that f of a is less than 0. We can see that f of b is greater than 0. Over here, f of a was positive, where f of b was negative. So they had to be opposite in signs, and then we're guaranteed a 0. So I still have to say I have the continuity piece. I still find f of 1 and f of 2, so find your function values at your endpoints. And then you're going to say, since one of them's negative and one of them's positive, I have a 0 in that interval 1 to 2. Okay, we looked at the practice problems here. So here, explain why it has a 0. So that's what we just covered. See last example. And on these, it's also the last example, but there's a little extra. Use a graphing calculator to find the 0 to 3 decimal places. Now, you have options while you're at home. You can pull up Desmos. There's also different graphing calculator emulators that you can find online, but I bet you if you use Desmos, you would be able to find it. And then these last two, you're going to be looking at the first three examples. And that should take care of you.